Amit Saha. Amit is currently a software engineer at freelancer.com in Sydney. He's the author of Doing Math with Python. So if you want to check out his book, he has a copy of his book here if you want to have a look at it. He's also the creator and maintainer of Fedora Scientific, a Linux distribution targeted towards computer users in the educational, scientific, and numerical fields. Thank you.
Thanks, Katie. Hi, everyone. Great to be here. So thank you for the introduction, Katie. So yeah, I'm Amit Saha, and thanks to Facebook, I've got this nice map here. So I'm from Sydney, here for the education seminar today. So I'm the author of the book called Doing Math with Python, which is so the title of the talk and the book are of same title, which is not a coincidence. So this book was published last year in August, I think, same time. So far, it has been translated to a few languages. I don't read any of the others, so I have no idea. But anyway, the covers are nice. So that's the Japanese translation, then the French, and the Korean translation. So if you're following along, you can go to this link. It's bit.ly math with Python, and you will get the slides as well as the demos. So if you go there, you will basically find this. So you can there's a README which you can download the zip archive and install Anaconda Python distribution. There's a basic guide which I have linked to, so you may find that useful. So the demos are all here. I should mention that all these demos are Jupyter notebooks, but besides a few like the interactive notebooks, I don't depend, none of these demos actually require Jupyter notebook to run. It's just easier, and it's a very good way to demonstrate during presentations. That's why they are just as Jupyter notebooks. And I'll jump ahead a bit just to show a few things. And slides which have associated demos with them would have this thing here, so you can follow along in the specific notebook. Okay, so with all that done, so why math with Python? I think I should give a bit of a background, and it is unlike to a lot of among you who have basic hands-on day-to-day interaction with students. I don't have that, so whatever I talk today and what I'm proposing today or what I've written in my book draws a lot upon my experiences 20 years back when I was learning to program. So when I learned to program, and I was obviously learning other subjects as well in school, what I felt was there was quite a bit of disconnect between programming as well as the other subjects that I was learning, as if programming was meant to be like a tool just to learn for its own sake and hopefully someday I'll be able to use it in something. Whereas other subjects were really important and everything else. So what happened was I saw two things. Some students, like me, I got interested in the programming part, but a lot of them did not understand, did not really get to programming because obviously they were not taught in a way that they could learn properly. And some of them dropped out. When they are given an option to opt out of the programming subject, they just opted out and opted for the other. But what I feel is if at that stage, if programming was programming was shown in a way that it could solve problems, or not necessarily solve problems, maybe explore other subjects, I think it would just make it more interesting for everybody. So to summarize, what I believe is integrating Python with other subjects, math and maybe others, would lead to a more interactive and enriching teaching and learning experience. So how do you do that? So the tools that you're going to use is Python 3. So I don't use Python 2. I don't try to aim for any Python 2 compatibility, just because I want to be forward-looking and somebody learning something new for the first time. They don't need to know what the differences are even. So the package which forms an integral part of my proposal is SympY. I'll get to that next two slides. And the third is matplotlib for drawing graphs and essentially animations and anything graphical. Those are the links you can follow along. So I should obviously tell just even before I start is how much math, what kind of math am I talking about? So the math I'm talking about is basic algebra, basic statistics, sets, probability, random numbers, a bit of probability, discrete probability mostly, a bit of continuous, but that is an application, so which I'll get later, and some basic calculus. How much Python am I talking about? I'm assuming that the reader or the student would know about defining and calling functions. They would know about loops and basic data structures. They would know how to create objects of classes, how to access an attribute of a class, and they would know how to call methods and objects. That's all my assumptions that I'm making when I'm making my proposal in the next slides. So let's get started. So Python so I have organized this talk into 3 different parts. Like first I show Python as a scientific calculator. Second, as Python as this really awesome calculator. And then I go into where you go beyond calculations, where you explore things which you wouldn't otherwise be able to explore without programming. So first is scientific calculator. I assume a lot of us among us here are familiar with the standard math modules. So greatest common divisor, pretty simple, factorial, or we can do things like validate simple known results, like when you're learning or teaching trigonometry, like this sine square theta plus cos square theta equal to 1. We could do this, so this I can see, like I have to convert the theta into radians because that's what all the trigonometric functions assume. And then a newly or more recent one is the statistics module, which has the basic statistics function. So you can do calculate the mean of a data set or the median of a data set. And then using this, you can use this as your building blocks and develop your own functions, of course. But what becomes more interesting is when you're using, say, the Python startup variable, you can define your own functions. So for example, here I'm using, I don't know how much of it is visible. So this is I'm starting the idle editor. Idle 3 is the Python 3 version, of course. And I'm just specifying this file, which has some of my functions defined. So when I start the interpreter now, I'm going to have so this is a function which I have in that file. It's just a simple basic unit conversion function. So when I start the Python interpreter, I have all these custom functions ready for me to use. So I can basically say, okay, what do I want to do? And similarly, I think I have another function defined, but anyway. So that's the idea, which is you can use the built-in modules and write your own functions, your custom functions, whatever calculations you may need to do all the time. So what it gives us is we don't need to do this import math. We don't need to import the module itself. It is already there when you start the interpreter. Okay, so question time. If I were to tell you that you need to write a program which tells you this, enter an expression in X to graph, the user inputs that expression and creates this graph, how many lines should this take? Any guesses? One line? Sorry? No, using pure Python. You said 1. How would you do that?
Would you load up like matplotlib and then above that just the basic linspace?
Yeah, that would be one approach, but that would be that's definitely one approach I would take, which is generate these numbers in a certain range and then plot it. That would be one approach. I don't know how many lines that will take, but I'll show an approach in a few minutes, which will basically allow you to. But the problem is, the problem with that is the function that you're trying to plot, that would be needed in your program. You wouldn't be able to take x squared plus x plus 1 as an input, right? So that's a drawback. I'll show you a program in few minutes, which is 4 lines, and it allows you to enter any expression in X, and it'll draw the graph. Okay, so to do that, which is where I start my second part, we'll need SymPy's help. So I'll start off with some SymPy basics. So this is SymPy, and a basic idea in SymPy is how you represent symbols, and symbols mean X as in algebraic X, Y as in algebraic Y. to make our Python program understand x as x and not a variable which needs to have a value, we have to create an object of symbol type. So this is what we are defining. So this is the x symbol, and this is again another object of the x symbol, although I'm calling them differently. So when I do x plus y, it knows that both of them represent x, and it prints me 2x. So that's the basic idea. Okay. Some more basics of sympy. So we know what this does. We know what these two lines do. Next, we define an expression. So this is how I can define an algebraic expression in Python. I just say 2x plus 3x squared, and it's in a form and let's say I have defined this formula, right? And then I want to know what is the value of this expression when x is, say, 1. And to do that, I have to use the subs method, like substitution. And it is used to provide basically the value of x that I want to substitute. So it essentially means that, okay, my book is not happy. Yeah. So it essentially means that I want to substitute 1 in place of x in this expression. And once I run this, you'll see a value of 5. So that's how you substitute. That's how you find the value of an algebraic expression. Okay, that's then okay, this is a slightly longer program, and which basically builds up to our plotting program. So here what I'm doing is I'm going to demonstrate how. So the input function, which allows you to take, like, basically provide inputs to your program. So when you provide an input to a program, whether it's an integer, whether it's anything else, it goes as a string. So which is basically when I input something like this, to Python it is a string, something like this, and whatever I give it. But in this form, it is not understandable by sympy. So I cannot say sympy to manipulate this in any way. So what I need to do is I need to use this function called sympify, which basically converts this string to a form that is then understood by sympy. And you can see an example here. What I have done is I'm creating this so-called simplified version of this input, and then I'm calling this function called factor, which basically factorizes this algebraic expression, and then I have the factors. Okay, so that leads me to the create a graph program. So that's your 4 lines. So in fact, I don't even need this 4. This is not even needed. So that's actually 3 lines. So I don't need this either, but I'll leave it here. So I'm going to do this first. For those not familiar with Notebook, I need to do this so that the graphs are displayed in line. When I run this, it'll ask me to enter an expression, which will be hopefully soon. Just when you want them to work. Yeah, that's exactly right. Okay, so I'm going to do something else. Let's say x sine x, and here we have a graph. So yeah, so that's 3 lines. And it's not limited by what function it's going to be able to plot. You can give it pretty much, as long as it's of a single variable, it'll do it. Okay, I'm definitely running short of time. And you can do things like solving equations. Once again, the number of lines is, well, you can't, again, 3 lines, so that's all you need. So you just call this solve function and it'll get the solution for you. Okay, I'm going to go a bit express now. So this is for inequality solving. Now this is a very long program, and the reason for that is it can solve any kind of inequality, like whether it's a rational inequality, whether it's a polynomial inequality. So that's why I had to write this big program to just account for all the different inequalities you can have. And once again, pretty similar interface. It asks you for the inequality, and then it will give you the range, the solutions that solves the inequality. Okay, so that's done. Okay, so how many lines would this take? Finding the limit of a function, like, which is, any guesses? Okay, I'll stop the suspense. Once again, 3 lines. So all I do is, this symbol is now familiar. Limit is the class. Well, yeah, it's a class. The class which is responsible for, not responsible for, like, which is going to be useful for us when you want to find the limits of functions. So all I need to do is I create an object again to represent that x is x. I'll get to that in a minute. But the more important point here is, here what I'm telling is I want to find the limit of the function sin x by x as x tends to 0. So when I just create this and I run this cell, I get this expression which is very familiar for like all of us when we learn to do math essentially. And this magic happens because of this init printing system. This is basically Sympy's own function, right? So it basically detects that it's a notebook, and so it renders it very nicely. That's using MathJax again. So as you can see here, it is not actually calculating the limit. It just shows that, okay, I'm going to calculate the limit. To actually calculate the limit, I have to call the doIt method, and then I have the result. Similarly, for derivatives, once again, pretty similar. Here, instead of the limit class, I import the derivative class. Again, I give a function, it prints it, like basically shows what it's going to calculate. And then again, I just call this doIt method, and it gives me the derivative. So the parameters to this class is, the first is of the function itself, sin x by x. Second is the variable with respect to which you want to differentiate. If your function has multiple variables, it would then calculate the partial derivative with respect to that variable. And and next I have integration. Once again, pretty similar to how we have been doing so far. We import the symbol, we import this integral class, we give the function, we call the doIt method, and out comes the integral. So that was indefinite integral. This is how we do definite integration. So the first is the function itself, and then we specify the variable and its limits. So this is a tuple. So I'm specifying here essentially, basically this written in a form that Python understands. And again, doIt function, it creates this. So as you can see here, it gave me sometimes friendly features become unfriendly, like so. It's vanished. Okay. Okay. So this, you will see that I have this eval f function after this. So basically, sometimes SympY will give you the result in a form which is not in floating point. It basically it's in an abstraction which SympY has, so it's not directly a floating point variable. What you can do is then you can call this eval f function, which gives you the floating point result that you may want to reuse in another calculation. Okay, so I've gone through this. Okay, but can you do more? Like so far, what you have seen is we can use Python to build basic calculators and really smart calculators. We can certainly do more, and to do that, what we'll do is we'll take help of. I think I'll skip this over for now. We'll take help of interactive notebooks, and by that, what I mean is something like this. So this is an example of drawing a fern. Now this combines non-uniform probability, which is well, one of the things I was going to discuss, but I don't have the time to, this combines plotting graphs. This combines interactive widgets. So when I run this, hopefully, I'll get a nice slider. Kernel starting. You would imagine everything would work. Okay. So when I run this program, I have this slider, and what this is essentially doing is this specifies the number of points in the font that you want. So I can change this, and it'll automatically draw the font. So the magic here happens with this single function, which is this interact function. The first argument to that is the function that will be called. And you can see that it takes a single argument, and which is basically the value of the slide that you're choosing. So very basic, but it really creates a very interactive experience. And you can play with the number of fonts here, and similarly. What else do I have? Yeah, so I also have a demo of the Mandelbrot set. I don't think I have the time for it anymore. I'll show the projectile motion quickly. That was one of my favorite things in physics when I was learning. So,
Everybody's.
yeah. So, I also found a way to have this. So this is one example of where I don't need notebook for showing this, but it's just obviously a more seamless presentation experience. Kernel starting. Anyway. So while the animation starts, what I'll do is, so I want to talk about a bit. And what I will talk about is, so we have seen a few examples of how we can integrate math and Python programming and even maybe science or other subjects. It also gives us a good base for exploring other subjects like data science and machine learning. In fact, one of the demos that I have is something called of a gradient descent method. So the exact functions that I used for the derivatives, I actually used it to implement gradient descent. And then, so after that, I implemented to use a simple linear regression. And all I'm doing is I'm just using Sympy's own method. So I'm not having to calculate any derivatives numerically or provide the derivatives by hand. I'm calculating everything in the program itself. So I think all of that is a very good base for learning all these more even advanced things. Okay, let's see. I don't know. Okay. I have to show that. Let me see. It has decided it's not going to work, so maybe I'll try and run around the demo. Wow, this is like a super fail to so,
There was a talk about internet failing and how many things.
no, it's not. It's not internet. It's localhost. It's all localhost.
Localhost.
Yeah, it's localhost is failing. It's okay. Well, the animation happened and we didn't see it, but anyway. So when I run this, so yeah, I mean that's that. I think what this allows us to like basically experiment with projectile motion, understand what happens when you change the initial velocity or you change the angle. Here I have specified like the fixed initial velocity of 60 and an angle of theta, and so basically allows us to explore various things without having to go to the field and throw balls. Like so that's an okay. I'm going to give one last shot at making this work. In the meantime, if you have any questions, please feel free and ask so that I don't waste time.
Okay, round of applause, and then I'll grab some questions. Any questions? Or do we just want to see the next cool demo?
Actually, I don't know. I could show you gradient descent.
Yeah, we've got a question.
Works.
If we were to like show this to students, would we be asking them to look through the code and see how it's written before they just play with the program? Would that generally be it? And so does those little smart calculators have like things that you can cut and chop and allow the students to maybe build their own sort of things?
Yeah, pretty much. I guess that's pretty much the idea. Like, so I guess explain the math a bit and then basically show what it would look like in a Python program, and then build upon it, and that's pretty much the idea.
Is the Jupyter notebooks like a requirement, or can
No,
other
not
IDEs
at all.
be
No,
used?
not at all. Like, so the main reason I've used it, it's just easier to, because it's seamless. I have the output there, so it's not a requirement. Except for the ones where I showed the sliders, those are Jupyter Notebook features. Yeah.
I mean, one of the challenges that we've had when we show this kind of stuff to maths teachers is they come back to us with statements like, "Oh, but if students haven't done 100 simple differentiation problems, they're not going to actually know what differentiation is," which I think is ludicrous, because getting caught up with the computation aspect of it takes away from understanding the math. So how would you propose, once a student's built something like this, teachers, I guess, investigating this in a more kind of genuine, real, applied way? Like, how is that going to change, or what implications is that going to have for what they actually do in maths class, and how are they going to cope with that? Because I would argue that it meets the needs of the Australian curriculum better than their current practice does, but they may think otherwise.
So this is a proposal. Obviously, I don't have any experience. So the way I guess it would work is, first they learn the math, right? I mean, obviously, you would need to know what the derivative of sine x is, for example. I think the next step would be to use that in some sort of a practical way. Like, for example, use it in a way where you would use that. So once you know already what the derivative of sine x is, there's no point in in a program, you can just make a program do it once you know the math. So I guess, for example, like the gradient descent method is it sounds very fancy, it's big. I didn't learn it in school. That's all absolutely true. But I think that's a very good way to apply that in a context where you don't need to worry about knowing the formulas anymore. You know the formula, you just want a program to do it. But once you make a program do it, you know that your programming class is going to be also useful for doing all these other things that you're learning, not necessarily limited to like solving like printing a Fibonacci series, for example. So yeah, it's fuzzy. I know. Like it would be like you're trying to substitute like students like pen and paper experience with programs. But yeah, I think there's a somewhere in between where I think it would just make the students more interested in both subjects that way.
Okay, yeah.
I'm a teacher, but I never used Jupyter before. So if I want to try this, where should I start, or you have a book to recommend?
I don't know actually about books with Jupyter Notebook, but you could easily start. I mean, you could start simple, right? You could start with something like this. So ideally you would write this in a program. Let's say you would write a program, you would write it in a file. Yeah.
Or the mechanics of actually getting and running.
Yeah. Oh, okay. So are you? Okay. So I'll get to that next. So if you have to do it in a program, you just write these files in a file and then run them either in your IDE or using the Python command line. So you could start with like this, right? Instead of doing this, you could write it here. And then you have that output. So I think this is the kind of, you could start it this way, and then you could probably, there are other projects like NB Grader, which people use for classroom grading. So there are all sorts of things. So I guess that would be one approach. The way you'd get it is, I think Anaconda node, are you familiar with the Anaconda Python distribution? Sorry? Yeah. So if you download that, you would get Jupyter Notebook straight out of the box. So all you need to do is run this command, like, not sure if you've seen. So here, for example, all I'm doing is, it's lost somewhere.
Down,
Jupyter Notebook.
down a bit, up a bit.
Okay, yeah. All I'm doing is running a single command. It starts, it's a server program, so it starts and then your browser window opens and it shows you like all these files that you have. So yeah, I guess you could start that with simple. I mean, I'm not experienced Jupyter Notebook user either. Like I have just been using for my demos and everything. So, but there are resources, a lot of resources which basically would help you. I think there's a Jupyter for Teaching Google group where people can recommend things.
Cool. One more question.
It's sort of really a part answer to the question about trying out Jupyter and getting it installed. One thing that's useful is there's a website called Wakari, wakari.io. It's basically a notebook server running in the cloud that you can just sign up for an account and you can just play with it without having to install anything and figuring that out. So it's a good way of sort of kicking the tires before you learn a bit more about how to get things installed.
Cool. All right, any last questions? Okay, thank you, Amit.
Thank you. So all the demos that didn't work here would all work if you try it locally. So yeah, give it a shot and you feel free to use it in any way you feel possible. There's no licensing restrictions or anything. So as long as you get something useful out of it, it'll be great. Thank you.